Yeah, okay. Thank you for. Yeah, okay. Hi. Hello, all. Good evening. We discussed it, no, yesterday, design. Whether it is shared or not.
Shared.
Not. Okay. Okay, then. Thank you. Okay, then, as I told you yesterday, today we will discuss on that verification part. Okay. So I will share the screen. Okay, my screen is presenting now. Hello. My
Yes,
screen
sir.
is presenting my PPT. Okay. Okay, as usual, we will start with a quick lecture, okay? Like what we saw in the previous sessions and all, okay? So what we saw is introduction of RISC-V. Okay, RISC-V in the sense it is a ISA. ISA in the sense it is a instruction set architecture. So if we need to do a process, there should be a instruction to guide them, okay? So that instruction is there are some different types like CISC, RISC and all, okay? So here we are going to see RISC. Why RISC in the sense? It is simple, okay? It is simple to use and it is open source. And one more thing is, it is we can how can we say means it is like risk we know risk we in the sense they are updating, okay? It is like fifth generation, okay? And it is used in a lot of places, okay? And this is risk architecture. As I told you before, instruction memory, that is it will store the instructions, and to fetch that instruction we have instruction fetch unit, and then for controlling that instruction, we use controlling unit, and that control unit will take care of the instruction fetching, and it will control that ALU also, okay? Then after that, memory data memory. As I told you yesterday, data memory is to load some data to the register and to store some data, okay, in the memory location of the data memory, okay? So this is the difference between RISC and CISC. As I told, RISC is easy and simple. CISC is somehow complex, and in RISC we have fixed length. That is, our instruction length will be fixed. Okay. So as of our syllabus, we are going to see RISC-32I, and there are some extensions. In our project, we are using I extension. I extension in the sense it is integer. Okay. And there are multiple extension like F means floating, M means multiply, divide, and D means double precision. Okay, these are some extensions, and these are some base ISAs like RV32I in the sense RISC-V, which is of 32-bit instruction, and it is I type, that is instruction type. And we have some versions like RV64I, RV128I, like that. And it has RISC-V at this is our project, no? RISC-V 32I, and it have 32 general purpose registers, 32-bit fixed length instructions, and it have store load architecture, and we all know it is used in plenty of places. And these are the instruction formats like R type in the sense register to register. Yesterday we see, no, in design, that is what it is. I means immediate operation, S means store instruction, and B means branch type. That is, we will branch the instruction. Like if we have a location, okay, we move on to that. That is called branching. If we have a data, it is not the actual data. It have some address. Okay. So if we go into that address, there will be some data. It is called branching, and we have upper immediate and unconditional jump. And these are the frame formats. As we discussed yesterday, there is opcode, and there is different frame format for different instruction formats. Okay, so these are the frame format which is of 32 bits, and there are for different extension for different instruction formats. We have different frame formats. So these are the different frame formats like R type, there is different frame format. For I type, there is different frame format. And this is for S type, and for B type and U type, and we have J type. Okay. And I think I have shared this PPT also, so you can refer that as well. And what is pipelining? And as I told you, pipelining is for overlapping the instruction. If we have multiple instruction, to reduce the time which we consume, we will overlap the instruction. That is, if an instruction is in fetch stage, okay, and it is moving to the decode stage, the second instruction will come into the act, that is, it will come into the fetch stage, okay. And when our first instruction move to the execute state, this second instruction will come to decode stage, okay. This is what pipelining is of, okay. Pipelining means overlapping multiple instructions, okay. And then there are some advantages of fixed length instructions, and it is easy to decode and every instruction is same size now, so we can easily align, okay. There will not be any problem in the alignment, okay. And simpler pipeline design and hardware design also decreases. We have simple logic and faster instruction fetch, because faster instruction fetch and decode because of the fixed length, okay, fixed length of instructions, okay. And then there are some real world companies, okay, which are using it, like Nvidia, Google, like that. And at last conclusion, we all know why we are using RISC-V, and it is using in plenty of places. And this is what we see day before yesterday, okay. This is theory part. I think you are all familiar with that. And in this design part, we see yesterday, no, why is this ALU controller is off. Wait 1 second. Yeah. And I think you all get the idea, no? Why is this is for and what is the purpose of this? Yeah, you all understood, no? Yesterday's coding part. Is there any doubt or anything to clarify? Is there any doubt on yesterday's coding part, the design? No doubts, sir. Is there any doubts regarding this yesterday's design part? Okay, then we can move with the verification part today. That is, wait 1 second. Okay, today we will move with verification part. Before that, I will once again overall explain, okay, what is the code is of and why we are using it. Okay, as I told you yesterday, this is ALU controller. So ALU controller in the sense, anyhow, we are going to perform some ALU operations like AND operation or operation like that, add, subtract, like that. We have plenty of operations. Okay, so like that, ALU controller will control like what operation we are going to do, how it is going to execute, what is the function code 3. Based on that function 3, it will select based on the function 3 and based on the ALU operation signal, it will select which operation need to do, like that. Okay. This is what the ALU controller is of, and there is a controller. It is going to control the opcode and it is going to control the instruction. Like for this opcode, which are the signals should be on, which are the signals should be in low state, like that and all. This control unit is going to control based on the opcode. Okay. And see here, for example, for load word, there is a opcode which is of 00, 000 and 11. Okay, and see, opcode is of 7-bit length. Okay, so is there is a opcode which is 00, 000, 11. What they have mentioned here, it is a load word. So what is meant by load word? We are going to load some word into the register where we are going to fetch them in the memory. Okay, so memory to reg, that is we are going to somehow we are going to take the data from the memory and we are going to store that in the register. For that, this memory is that memory to reg signal is on in high state. And for memory read, we are not going to perform, but you can see here store in the second instruction in store word, that is this opcode 001 000 11. This opcode is for store word. Okay, so store word in the sense this memory right now, this is on. Why this is in high stage? Because we are going to write something in the data memory. Okay, that is why this is on. See, remaining signals and all are off stage only. And this ALU operation will be have some other codes because it is going to choose what operation is going to perform. For example, see here first in this block, in this ALU controller, first 3 bit is for function 3, but the second 2 bits, no, this last LSB, okay, LSB and the before and the after bit which follows the LSB. Okay, this last two bits now, this will decide what operation we are going to do. That is called this ALU operation signal, and this signal is here. Okay, here only we are going to decide what is going to happen. Okay, so this controller is for controlling purpose. Okay, I think you all can understand as I explained yesterday. And this is of memory, data memory. As I told you, data memory is for storing purpose. We are going to store some data, and in case we need, we will load them to the register, and from register we are going to use for our ALU operations. Okay, and if we need to store some data, we will get the final result, and in case if we need that result for further purpose, we will store it in the data memory. Okay, and we have flip flop, and as I told you yesterday, we need flip flop. Why? Because we have PC, that is program counter. And what is the operation of program counter? It is to, it program counter have the address of the next instruction to be performed. Okay, it have the that program counter have the next instruction which is need to be performed. Okay, so we are using data flip flop. Why? In the sense, we need to transfer the same data which is in input side, the same should be come in the output side as well. Okay, for that we use D flip flop. And why we need this flip flop is in the sense, we need flip flop because of the synchronization. At right clock time it should happen. Okay, at right clock time our PC should be transferred. Okay, our PC should be execute. For that we use flip flop. Okay, and immediate generation. Immediate generation in the sense, see, we not only going to pass any data through register, we also pass our inputs immediately also. Okay, so for that purpose we use immediate generator, that will immediately generate, okay, whatever we need, that immediate value. So for generating that immediate value, immediate generator is used. And see here, here it is performing the extension operation as I told you before yesterday. This MSB bit, that is of sign bit. If the sign bit is 1, the remaining bits will be extended as 1. If the sign bit is 0, the remaining bits will be extended as 0. Okay, this is of extension. Okay, and using this we will generate the immediate value. Okay, and this is instruction memory unit. See, we must be careful while seeing this, because in our verification we need to do some decode here. Okay, I will explain why, how it is verifying that things and all. So here our instruction memory unit, no, it holds the instruction which we need to perform. Okay, so here, see here, you can note now this instruction memory unit, and see, as I told you, there are 64 memory locations. Okay, so this 64 memory location, each memory location is of 32 bits. Okay, so there are 64 memory locations, but in this code, okay, in this code particularly, we only used 20. Okay, 20 memory location is used. Still there are 44 memory location. If you need to customize, you can customize it. Okay, it is customizable code only, but there is right now for our purpose we are taking 20 memory location. On for 20 memory location we have separate instruction to do separate operations. Okay, and each memory location is of 32 bits. Okay, and see, this memory location is important for today's verification session. Okay, as of now I didn't move to the verification session, we are just explaining the previous things. Okay, and see here it is mux. Why we need mux? To select some data. Okay, we are selecting because sometime we will pass some data immediately, and we need a data which we need to select, either it is D or D1 or D2, or sometime we are going to select, we have wait, I will show you in the top layer. See here in this mux, see here there is reg data, there is immediate value. So we can select what we want. We can select, either we can select immediate value or we can select reg data. Okay, using this mux. So how we select? Based on our need. If we want to pass some value immediately means we use this mux. Okay, and there is reg file. Okay, as I told you before, why we need reg file? Because of this ALU operation. See, you must be strong in one thing. Here the operation will be we are going to, in order to perform ALU, okay, we are going to load the data from the data memory to register, and using that register values only we are going to perform ALU, or we are going to pass the values, input values immediately, okay. Other than that, we are not going to perform the ALU operation using the data memory directly, okay. This is what here it is, okay. And then ALU 32 in the sense, as I told you yesterday, ALU which is of 32 bit, and it is going to perform the arithmetic logic operations like AND gate, OR gate, and there is addition, subtraction, which is of signed bit, unsigned bit, like that. They have some combinations. They have equal to, they have less than or equal to, comparison, like that. See here, for every arithmetic logic unit, there is an instruction and which it need to be followed. That is ALU select. And see, in this data part, we can compare, okay, like where this ALU select is go. As I told you yesterday, see, we must refer this top layer, okay. Here, these are the signal connection, and see, there are two types of instantiation, okay. One is by name, okay, by name. It is instantiated by name, okay. Second one is instantiation by order. That is, I explained yesterday using that paint. Order in the sense, whatever order you give in the actual design, that same order should be followed. Or you can follow the name. Name in the sense, you can alternate, you can deorder. Like what I'm telling to say, what I'm saying is, you can you can you no need to follow the order in case if you use this name alignment, okay. In case if you instantiate using name, okay. In case of name, here they used that, they have they instantiated in the name format, okay. Okay, then this is of the first code which we saw, and there is second code which is of 32 which is of 16 bit. And as we discussed yesterday, the same whatever is there in the 32 bit, same will be here. See here, I will explain this once again, and after that we will move to the verification part. Okay, just a overview. Suddenly, if I go to verification, means it will not be good, no? So for that, so ALU, okay. So here, as usual, we have two inputs, and there's a ALU controller which is going to tell us what operation is going to perform, like addition, subtraction, like that. And here we have a result. A result is like default. If you are not selecting anything, the defaultly addition will happen, okay. And we are assigning zeros, and this data memory unit, okay. So in the previous design itself, we come across the data memory unit, and what is the use of that. Data memory unit will store some data. Why? For later purpose, or right now if we need some data, we can store or we can load from the data memory, okay. So the same signals you can come across, okay. I think you are all familiar with this now. At least not too much familiar, at least just know what you should know, okay. What is that, what is data memory is, like that you should know, okay. And then there is a register. As I told you in the previous design, why we use register to load some data and to load some data, okay. And after loading that, using the registers, we are going to perform the arithmetic operations, okay. So for the loading purpose, where will we load, where we get the data? From the data memory, okay. So from the data memory, we are going to load some data, or we will pass some data immediately, and we are going to perform the arithmetic operations, and these are the parameters, these parts, okay. So parameter in the sense, we are going to give some constant value. For example, see here, column we declared as 16 and row we declared as 16, okay. So since we declared here, what we use is, wait, I will show you. See here, in the data memory, we are just declaring this column and row. Instead of declaring every place like 16, 16, we will declare like this also. Okay, see here, we included that parameter file, and then we are declaring like column and row. Okay, and then we have data path. Data path in the sense, see, one important thing is, as I told you in the slide in the PPT, wait, I will show you. As I told you in the PPT, data path will have the ALU and register file. Okay, data path will contain that, and it have some it have connection with, not some connection, it have connection with data memory. Okay, so data path have ALU and register file. Okay, see here, data path, and inside the data path, see, we have instantiated many blocks here. See, instruction memory, mux, and here we have register file. Okay, and we will instantiate this ALU. Okay, see here, as I told, this data memory also instantiated. Okay, so according to this PPT, this data path will have ALU, register file, and data memory. Okay. Okay, now we'll move to this control unit. So why this control unit is used for? Because it have some opcode. Based on that opcode only, we are going to perform the instructions. Okay, that is what type of instruction format it is, and what that based on that opcode only, we will select the signals. What signals should be selected? What signals should not be selected? Like that and all. Opcode, this control unit only decide and tell. Based on this only, we will do the upcoming operations. Okay, so this is test data. Test data in the sense we are keeping this data for testing purpose. Okay, and we have ALU control, as I told you in the previous design. ALU control is for controlling the ALU operations. Okay, we have arithmetic logic unit now. So in the inside that, see here, inside that it will perform the addition, subtraction and all. But we need some control, no? So for controlling them, this ALU control will be used. Okay. So the outputs which we give here, okay, see here, the ALU control is equal to 000. Okay. It will be passed to this ALU. Okay, actual ALU. See here, this 000 is passed here. So based on this signal, it will perform addition, it will perform subtraction, like that. Okay. Then we have test program. It is also for testing purpose only. Okay. Then at last we have some, we declared the instruction memory. Okay. Then you can ask, see, in the previous design, inside the instruction memory, we have various instructions, but here we have no instruction and all. You may have a question like that. For that, see here, they have the instruction memory here, and they just take the file here. Okay, they used the file here. Okay, so as usual, mux is for data selection. Whatever data we need, either we need reg data, or we are going to pass immediately, that we will select using this mux only. Okay, see, as of now, design is over, and I think you all understood. No, is there any doubt till now? Once again, I explained you just a overview of the design. Yesterday we explained detailedly. I explained detailedly, and today also somehow I tried to cover up all this topic. Whatever we saw till now, I just we just had a look on all the topics. Okay. So till now, is there any doubts for you or any questions to ask? Anyone? No doubts? Are there any questions?
No, sir.
Okay. Okay, then now we will move to this verification part. Okay. So as I told you yesterday, okay, we are here, we are going to see two verifications. Okay, one is of Verilog and one is of System Verilog, and I will explain what here going to happen. Okay, right. As I told you in this session, this instruction memory will going to play a major role. Okay, see here, here is a module TB, that is test bench. Okay, as we all know, we are going to pass clock and reset here, and finally our result. This is our result. See, usually here in this test bench, what we are doing is we are going to check whether all our instructions are covered or not. See, we have 20 instructions, and we are going to execute all this 20 instructions, and here we are going to check whether all our 20 instructions are executed or not. That's all. We are not going to check anything else. We are just going to check whether all these 20 instructions are executed or not. Okay. So see here, we have instantiated the processor. See, you all remember, no? Yesterday I told processor have the all the major blocks and it is the main one. Okay. This processor is the main design which holds all the major blocks. Okay. Everything is main, but this processor will hold everything. Okay. So we are instantiating the processor here, and one second. Okay. See here, as I told you, there are two types. Okay. Actually, what here we are actually what we are performing here, we are performing port connection. Okay. So there are two types. One is port connection by name. Okay. That is, see, once again I will explain. Okay, because we all need to know. No. See, if we have a design. Okay, module. Use the- Okay. Okay. See, if we have a module like mux, okay, and inside that mux we have input 1 comma input 2 comma we have a select line and output. Okay, and here we will do whatever. Suppose those unit, and here we are going to perform whatever we need. Okay, we are going to perform the mux operation. Okay, so after, while we instantiating in the module TB, okay, we can instantiate in two types. Okay, that is mux dut, and how we will instantiate is we are just, see here we will use like reg I1 comma I2 and s, wait here, um, I1 comma I2 comma f, and here wire y. Okay, so here we will instantiate in two types. Okay, one is port connection by name. Okay, port connection by name in the sense we are and one more type is port connection in by ordering. Okay, by order, port connection by name, port connection by order, port connection by order in the sense the same order like I1 I2 s comma y. Okay, port connection in the name in the sense we can change the order because we are going to connect according to the name. That is, see, dot I2 in the bracket we have I2. Okay, and then dot I1 in the bracket we are going to have I1. Okay, and then dot s in bracket we are going to have s, and then dot y in the bracket we are going to have y. Okay, so this is port connection by name and this is port connection by order. Okay, so this is what, this is the instantiate, two types of instantiation in the port connection. When it comes to port connection, I'm not telling this is the two types of instantiation. Inside that instantiation we have port connection. No? So there are two types and these are the two types. Okay, okay, then we come to the actual design. See here, always begin hashtag 10, then clock is equal to inverse of clock. So what we are doing here is we are generating the clock pulse, okay, which have 10 time unit. So 10 plus 10, 20. Obviously, our clock, one pulse will have 20 nanoseconds, okay, because 10 for high value and 10 for that is 10 nanosecond for clock high and 10 nanosecond for clock low. Okay, so totally one clock pulse will have 20 nanoseconds. Okay, okay, and this is here we are just instantiating, that is initializing. Okay, in starting stage our clock will be 1 and our reset will be 1, then our reset will be 0, then according to this always signal in this always block, according to this block our clock will be turned on that is turned to high. Okay, when the correct time, that is when 10 time units comes, it will turn high. Okay, so see here, this is the important part. Okay, see here. Wait, I will take the notepad as well because I need to explain this. This are actually it is little bit confusing, but I will explain. Okay. New. Okay. See here. What is the
One
first?
small doubt.
What? Ah, yeah,
One
yeah, yeah,
small doubt I have.
yeah,
Just a general query. In here, in the design, you have
mm,
saved all the files as .sv.
yeah.
Is there any purpose of that? I mean, I always said for design files I've seen
Oh, you
.v.
will dot p. Yeah, yeah. Actually, dot p is for Verilog and dot p is for system Verilog. That am I right
Yes,
now?
yes, yes. Yes,
Yeah,
yes. But
but
these are the design files, right?
yeah, this is design file only. According to this is EDA, no? See, wait, I will show you. This platform, this EDA playground, no? For this, see here, for design, they have given like design.sv. It is default, okay?
Oh, okay.
Okay, default they have given. If we need to change, but I don't know whether it is if we have some V extension. That is, yeah, I also used some
Mhm.
compilers. Okay, like Fasta Sim and all I used there and all. I
Mhm.
also used like .v extension only for verification, which is used of Verilog. We use .v extension only. But when it comes to this
Mhm.
platform,
Yes.
it will basically produce like design.sv. Okay. So it will, according to this platform, it will not going to cause any problem. So we are using .sv only. It is default. Okay. This compiler default.
Mm.
But when it
Sure,
comes
sure.
to like some compilers, actual compiler, QuestaSim and Quartus Prime and all, yeah, we
Mhm.
all use like .v extension for design, and if we use system Verilog, we use .sv. Am I right now?
Yeah,
You
yeah.
also
Yes,
familiar with
yes,
that
yes.
only, no?
Yeah, yeah, that only. Just I thought, is there
Yeah.
any purpose? So that's
No,
why I've
no, no.
asked.
No, no.
Okay,
That's why
okay.
I showed you know. See, while opening new file also, defaultly it will come like
Yeah,
.sv
yeah.
only.
I also work in that only, but I never,
So
I
noticed.
mean,
Okay.
here. Yeah,
Okay.
yeah.
Okay.
Just now I
Okay.
noticed
No
when you
problem.
said it is the design files. Okay,
Okay.
okay.
Okay. Okay. Then see here. Uh,
Mm.
first we will explain this first instruction. Like okay. See, this is our output. Okay. So I will tell you how this comes. Okay. And for this, what they have given is see in the comment what they have given, it is going to perform AND operation. So when we go to this instruction memory, which instruction is for AND operation? This first one. Okay. See, they have commented here now. This first one is for AND operation. So this first instruction is for AND operation. Okay. So here this AND operation is there. Okay. So first what we are going to do is we are going to extend this hexadecimal into the actual binary. Okay. See 00007033. Okay. So while extending it, what we will get? We will get 0000 and 0000000000, and then for 7 0 1 1 and again 0000, and for 3 we will get 0 0 1 1 and once again 3 0 0 1 1. Okay, this is the extension of this instruction. Okay, so now what we are going to do is we are going to this PPT and we are going to refer the frame format for I type. Okay, for R type. Okay, why? Because R type, this is going to perform with the registers. Okay, wait, see, according to R type, first 7 bit is of opcode. Okay, so this 7 bit, okay, this is for opcode. Okay, and what they have mentioned, see, then from 7 to 11 it is for destination. Okay, so from 7 to 11, okay, 8 9 10 11, this is for destination. Okay, wait, sorry, it will have 5 bits. Okay, and then this 3 is for function 3. Okay. And then this 4-bit is for source register 1, and next 4-bit is for source register 2, and the final bit is for function 7. Okay, wait. First 7-bit is for opcode, and then next 5-bit is for destination register, and then next 3-bit is for function 3, and then next 5-bit is for source code register, that is source register 1, and then next 5-bit is for source register 2, and next 7-bit is for function 3. Okay, I think as of now you all understand. Then next we will pass like, right. See, let's decode this. Okay, so our opcode is 0 1 1 0 0 1 1. Okay, so now what we are going to do is we are going to search the opcode. See here in the controller there is opcode, no? And where is the opcode which we need? Okay, see here it is like 0 1 1 0 1 1 0 0 1. Okay, and see, notice this here also 0 1 1 0 1. Okay, so here the opcode is 0 1 1 0 1. So what it means? See what they have commented here. It is R type. So obviously it is going to perform register type. Okay. So you can understand, no? So based on this register, we are decoding. Okay. So that register is there. Now we are decoding. Actually, now there is a 32-bit instruction is there. Now we are decoding that instruction. Okay. Okay. What they are giving, what the instruction, what is the information given in that instruction. We are decoding. Okay. I will explain you this one, and you can decode. Okay, by yourself. No, this is easy only. No, see, I will explain you anyhow. Okay. See here. So as I told, this opcode is for R type. That is, we have confirmed that. Okay. Then the next 5 bit is of destination register. Okay, it is fully 0. That is, we are not using. It is in 0th place. Okay. Then this is our function 3. Function 3 is 111. Okay. Now we are going to see the function 3. So I think the function 3 is here. So function 3 is 111. So 111 in the sense it is going to perform, either it is going to perform AND operation, or it is going to perform AND I operation. Either it is going to perform AND immediate, or it is going to perform AND operation. But in our opcode, what it is there, it is like it is a register type. So obviously AND immediate will not come. Okay. So AND operation is going to perform. Okay. So then what is next? There is 5 zeros. So it is like RS1. RS1 in the sense register source 1, and it is register source 2. Okay. So both are 0. And finally function 7 is 0. 7-bit, all the 7 bits are 0. Now we need to go to the function 7, where it is. See, this is the decoding. I am also decoding. Okay. From yeah, I am also decoding. Okay. Wait, we will now we want to search where that function 7 is. Okay. So I am also searching with you, because we need to decode, no, what they have given like that. Wait, we will decode. See here, function 7 is there, and wait, we will. Function 7 is for this 25 to 31 to 25. Okay. And here we have function 7, and in the first type they have given like, see, where those. Okay. See here in this function 7. Okay. If function 7 is, all the function 7 is 0. Okay. And it is R type, and our opcode is R type, or it may be R type I. R type I means immediate register type, and one more data is going to pass in immediate. And if the function 7 is, all the function 7 is 0. Okay. So here you need to note one thing, like, see here. here our function 7 is 0, but our function 3 is not 0, no? Here, see here, our function 3 is 111, okay? So we need to search that where it is like that. So according to our instruction, see here, where it is, yeah, here. See, our function 7 is, all the 7 bits are 0 and we have 111. So for that, what is this 4 bit of? It is 4 zeros. And what is the output? We need to search here, okay? Okay, this 4 bit of ALU result like that. Okay, see, wait, I will show you. See here, ALU select. Okay, so wait one second. See here, there is our function 7 and our function 3. As of our instruction, all in the function 7, all the 7 bits are 0, and in function 3, we have all the 3 bits as 1. Okay, according to this, our ALU select is 4 zeros. Okay, then if we move to this ALU select, see 4 zeros are there. So what it means? It means AND operation. Okay, and you can notice one thing. See here, both the since our RS1 and RS2 have no data, here what our output will be AND 0 and that is 0 and 0. Okay, is equal to obviously 0. Okay, this is what the instruction is, and this is what we need to decode. This is how we should decode. Okay, anyhow, I think you have the course, so you can also practice. No, you can also decode. I just explained you for your reference. I explained you how we should decode and what is that is of like that. I explained. So see here. So now we move to this instruction. So what they have given here is, if my TB result is equal to 32-bit 0, what is it is? Wait, I will show you. See what we get, 32-bit. And what is the size of our memory? 32-bit. So all the 32-bit will be 0, 0, 0, 0, 0, 0, 0. Then it is 12, 16, 20, 24, 28, 32. Okay. Why it is? Because our memory location is of our data memory, no? That memory, each memory have the capacity of containing 32 bits. So our answer is 0. So obviously all the 32 bits will be 0. Okay. So what they have given is according to the first instruction. So where they have passed the instruction, see, I think now you can understand, right? They have given this memory and here they are expecting this output. Okay. So for the given, for the 0th and the given memory instruction, for the given instruction in the 0th location, we need to, they are expecting this output. Okay. So if they are getting that expected output, their point will be increased to 1. Okay. So like that, we have 20 instruction, and if all the 20 instruction will, if all the 20 instruction is producing the output which they are expected, then what happen is this point will be added 1 plus 1 plus like that. It will add, and it finally it will produce 20. Why 20? In the sense, we have 20 instructions, and what it means, all the 20 instructions are produced the output what we have expected. That is the meaning. Okay. So till now you can understand, no, what this output is of. Okay, see here, this memory. Okay, what they are expecting is they have passed some instruction in the 0th location, and they are expecting a output. What is the output? That is, they are expecting the all output, that in that output all the bits should be 0. This is their expectation, because for the passed memory, for the passed instruction, they are expecting this output. Okay. So how this output came? As I told you here, by this operation, the output 0 is came here. Okay. So if all the outputs are 0, that is, if the output is what they expected. If they get the expected output, this point will be incremented to 1. Okay, like that we have 20. Okay, like that we have 20 instructions. Okay, so all the 20 instructions should get the expected output. So in that case, our output will produce 20. Okay, wait, let us run this. So till now, is there any doubt? See here, number of correct test case is 20. Okay, so this is what this for this design we wrote this test bench. Okay, according to this design we wrote a test bench, so it should produce a output like this. If we need to customize, you can customize, no problem. Okay, so as of now, is there any doubt or any query, anything? If you have any doubt, you can ask, or if you need some any other information, you can ask. Is there any doubt like that as of now? Anyone? No doubts, sir? Then we can move to the next design now, next verification part. Is there any doubts as of now? No doubts, no? Okay. See, if you take the second code also, same will be there. Okay. But the thing is, we need to decode. Okay. See, for your purpose, I'm taking this second one and we should decode this second one also. Okay. So they are expecting like that second one should be, they are expecting the output that the second one should produce 1 like that. Okay. Wait, let's extend this. So for this 000, 4 zeros and 4 zeros, and for 1, 0001, and then we have 4 zeros, and then we have 4 zeros, and then we have 4 zeros, and for 9 we have 0 double 1, that is 1001, and for 3 0011. Okay. Okay. See, we have decoded our one more instruction. Okay. As I told you, the first 7 bit is opcode. Okay. So now we can go and search what is this opcode, what it is telling to us, what type of instruction it is. So it is, wait 1 second. Where is my pencil? Yeah. Okay. So what is the opcode is? It is 001 0011. Okay. Now we go to the design and now we will search. Okay. Where our opcode is, here it is. So 001 001. See here, it is here now. So what they have given, and now we can find now it is like a immediate operation. Immediate operation in the sense we are going to pass some immediate data. Okay, that is what the opcode is of. And now what we need to do means we need to go to this immediate and see here the next 4 bits, that is 7, 8, 9, 10, 11. Okay, the next 5 bit will have the destination address. Okay, and what about the next? And see, it will have function 3. Function 3 is, what is the opcode? Destination, and then see 12, 13, 14. So next 3 bits of opcode, that is function 3, not opcode, function 3. Okay. See, I am decoding in front of you only. Okay. Okay, we are decoding the second instruction. Why I am decoding is you should know how it is actually works, how it actually works. You should be familiar with this. Okay. See, not only for this, basically, if there is a 32-bit instruction, it will work like this only. Okay, we need to decode and we need to get what is the information, what they have given, like that. We should decode. Okay, we should know that actually. Okay, this is destination register, and then we have function 3. Okay, it seems function 3. Yeah, and in function 3, all bits are 0. Now what we need to do is we need to go to the function 3. where our function 3 is in the ALU controller. See, if all the function is 0, what it is going to do? Add operation. How the add operation will be performed? By passing the immediate value. Okay, wait, is there any other? See, here there is a function 3, and see here, add I, that is add immediate. As of now, we all know no, that our function 3 is 000, and it is a immediate operation. We all know no. So this is our instruction. According to this instruction, this is the function 3 operation. Okay, this is going to perform. Okay, then what is the next information? Wait, we will see. See, you should, I'm just decoding just 2 instruction. For your practice, you can do like 3, 4 like that also. Okay. So see here, next one is source 1. Okay. Where it is, yeah, here. And we can use this 7-bit. Avoid the last 7-bit because it is a function 7. Okay, we avoid it. And here it is. Wait, we will check. See, our how many bit it have? It is like 15, 16, 17, 18, 19. Okay, it is taking 5 bits. Okay, 5 bits from here to here. Wait. So this 5 bits, no, it is like RS1. So as of our uh, our instruction and our rules, this RS1 is 0 right now. Okay. So the remaining bits are immediate. It is not function 3 because I told you no before it is function 3 function 7. I told you no before it is for R type only. But as of this I type and as of this I type format, frame format, the remaining 20th bit to this 20th bit to 31 bit. Okay, there is around 12 bits from 28th to 31 location. All the 12 bits going to give us the immediate value, going to be which will replicate the immediate value. Okay, so as of our format, the remaining bits will be the immediate value, will give us the immediate value. Okay, so see here, we are passing 1, and here in our RS1 there is no data, it is 0. Okay, so finally 0 plus 1, our output will be 1. So in case of hexadecimal, what is the answer? This one is the answer. Okay, see, this one will be the answer, and this one will be the binary for that. That first bit is 1. Okay, and let's go and check what they have given in the code. See here, they are giving 1 here. For immediate add, they are giving 1. So we are getting the expected result. Okay, so that this case will be passed and our point will get incremented to 1. So like that, this 20 instruction will be executed and our output will be 1. Okay, now we will move to the next one. This is the system Verilog. Okay, see, in system Verilog, I think you are familiar with system Verilog and this blocks. You are familiar with system Verilog, no? System Verilog and the components like generator, driver, monitor. Anyone?
Sir, can you please increase a bit font size?
Yeah, sure. This okay, no?
Yeah.
And you are familiar with system Verilog, no? Like what are the architecture? Generator, driver, monitor, scoreboard, like that.
Yes, sir.
Okay, then it is easy. Okay, what will change? The way of passing the input. That only we need to check. Okay, wait, I will go to the block and wait, I will increase the font size. Okay, see, the first one is interface. Okay, so as of system Verilog, as system Verilog architecture, okay, test bench architecture, why we are using interface? To connect our test bench with the DUT. Okay, so see, here we are mentioning what are the signals actually we have in our design. Okay, we will mention it in our interface, and we have a clock here. Okay, we are passing the clock because we should have a generalized, that is, we should have a common clock. Okay, for that we are passing here in the interface. Okay, then see, this is the interface which have the signals, actual signals which we are going to use. Okay, and then second one is transaction. So you all know now why we need transaction. Why we need transaction is this transaction block will have what are the information, that is what are the signals we are going to transact, that is we are going to transfer, and what are the signals, and in here only we are going to randomize. Okay, in this transaction only we are going to transfer a data. So see here, they have mentioned all this as rand bit. Rand bit in the sense they are all going to produce some randomized values. Okay, this is what this transaction is of. And see here, for our convenience, we are giving some display statement. Okay, for example, if this is name, and we will use no in the generator block, in the driver block, we will see, and I will tell you. Okay, in that place, this function void display will be used there. Okay, so here that PC current value and the instruction, and then this jump BNE in the sense branch not equal, BEQ means branch equal, and memory read, memory write, ALU source. It will produce some data, no, according to the instruction and according to the current compilation, at the compilation time, at the runtime. It will produce, no. So that is, we want to display that, okay, for our reference. That is what they are doing here in this transaction class. Okay. So obviously now we have the connection and we have the transaction, that like what we are going to transfer, that information we have. Then who is going to generate this transaction? Obviously generator will going to generate this. Okay. So the generator purpose is to generate the transaction. Okay. See here, we have randomized the transaction and we have counts here for our need. We are customizing it. Okay, and obviously mailbox is here, no, and you all know, no, what is the purpose of this mailbox? This mailbox is to transfer data, that is to transfer information. That is, this mailbox is used for the transfer from generator to driver. Okay, in order to transfer data from generator block to driver block, we need a mailbox here. When it comes to UVM, we will use TLM ports. Okay, and I think you all familiar with it. Even though if not, you will learn. Okay, when it comes to UVM, you will learn about TLM port. There it is a different architecture with some advancements. Okay, here for transferring the data, we are going to use mailbox. Okay, and event ended means it is a triggering one. Okay, it is going to trigger. Okay, then we have function new. This is the procedure. Okay, we are going to create a constructor and we are going to pass this email mailbox here, this mailbox variable here. Okay, the actual thing is where we are going to generate the transaction, that is this block, that is this task main. Okay, based on this task main only we are going to generate the transaction. See here, repeat count. Okay, we given here, no, we can give repeat count, or we can directly give as repeat in the bracket, we can give 20 like that and all. Okay, so see, we are creating a transaction and we are going to if the randomization is performed. Okay, and this if see, usually what happens is we are going to generate some randomized transfers. Okay, so like and see here, the repeat count is here. Okay, so here instead of repeat count we can give 20 also. Okay, so see here, we are going to create a new transaction, and if our transaction is randomized, it is going to move on to the next steps, or it will be it is a fatal error, or error will be produced. Okay, So see here, trans display, as I told you no before, that display will be used in some place, that is displays. See here, we have a function void display, and see here, it will produce some name, no? So here we are using that. Okay, where it is right. Not only in generator block, in driver block, in everywhere we will use. We can use this function display. Okay. So see here, we are using this trans dot display because why trans means it is that display function is present in the transaction block only, no? So trans dot display and generator, it is indicating that that is our process is in generator. It is in generator block. That is our data is in generator block. It is in generating stage like that. For that information, this trans dot display is here. Okay. Then this is the main thing. We are going to put all our transaction in a mailbox. Okay. Okay. See here, next one is driver. And why we need to use driver? You all have some idea, no? What is the use of this driver? Like we generated the transaction and we need to pass the transaction to DUT, no, for verification purpose. Okay. So for passing our data to the DUT, we need driver. Okay. The driver will drive our data to the DUT. Okay. So here this driver will perform. See, same here. We have virtual interface here. Why virtual interface? Because the physical interface is static in nature, and our driver, which is inside a class. Actually, our class is dynamic in nature. So static can't communicate with dynamic. Okay. So to perform our uh, transfer, okay, to perform our transaction between the driver to DUT, we need some interface. Okay, for that purpose what we are going to do here is we are going to form a virtual interface. Okay, why virtual interface? It is also dynamic in nature and our class is also dynamic in nature. Okay, for that purpose we are going to form a virtual interface, and finally we will connect all the virtual interface into the actual physical interface, and that physical interface uh, will carry our verification data, will carry our data to the DUT, and the final verification will be received through monitor, and our monitor will check what are the data we are receiving, and our scoreboard, no, it will verify whether we are getting the expected data or not. Okay, see here is also this same mailbox and the same procedure constructor. We are creating the constructor, and then here, okay, what we are doing here is we are passing the inputs to the DUT. Okay, that is trans dot jump in the sense transaction. In our transaction, there is a jump data. No, there is a data regarding that jump. No, it need to be transferred to the DUT. How it will be transferred? Using the virtual interface. So VAF dot jump. Okay. So this is how driver will work. Okay. Okay. Now monitor. As I told you before, this monitor will receive the uh, output data of the DUT. Okay. Anyway, we are going to pass the input for the design. We are going to pass the input through driver, and we are going to receive some output. No, so that output will be received using monitor. Okay. So see here, for monitor we have virtual interface. Why? Because this monitor also have some connection, not have some connection. It also have connection with the DUT. Okay, because it is going to receive the output of the design. Okay, and see here there is a mailbox. As I told you, there is a mailbox, separate mailbox for this monitor to scoreboard, and this virtual interface is for connection between the monitor to DUT. That is our design. Okay, so we no need to confuse. This interface is for the connection between monitor to DUT design, and this mailbox is for connection between the monitor to scoreboard. Okay. Okay then. See the same procedure, but here you can notice a difference. Like, wait, I will show you. or it was here, right? Actually, here what should come is, it should come in an inverse way. Okay, wait. I See, here we will receive a data from DUT through verification. Through virtual interface, we will get the data from the design. Okay, we will get the verification. That is, we will get the output data from the design in the monitor. Okay, in monitor only we get the data. Okay, where the data is coming from, it is coming from the design. Okay, so for to get that output, we will use this virtual interface, and this virtual interface output will be passed to the transaction. Sorry, actually it is correct only, it seems. Yeah, here it is. Okay, see here. Yeah, it is correct only. So in the driver, we are passing our transaction data to the DUT using this virtual interface. Okay, and in the monitor, we are getting the data from the design through virtual interface. Okay, so where we store in the transaction in the mailbox. Okay, then only we will transfer that to the scoreboard. See here in the 40th line, monitor to scoreboard, that put transaction, that is, we are putting the transaction which we get from the design. Okay, so from the design we get some output, no? So that output will be put in this mailbox. Okay, that is, the transaction is putting in the mailbox, so it will be received in the scoreboard. Wait, I will show you. Transaction will be received in the scoreboard. See here, we are getting now in the 34th line, monitor to scoreboard dot get, that is, we will get the transaction. Okay, which is transmitted from the monitor. See here, which is transmitted from the monitor by using mon to scb dot put transfer transaction, and it is received in this scoreboard. Okay, and what is the nature of scoreboard? It will check whether our output which we received from the design is matching with the expected output or not. Okay, this checking, no, this is the process of scoreboard. It will check whether the output we get from the design is matching with the expected output. Okay, so for example, for your example, let's consider let's consider this load operation. What they have given here, our reg write should be 1. Yeah, it is true, because our register write should be 1. Because while load operation, what we are going to do, we are going to fetch some data from the data memory and we are going to write it in the register. Okay, for that we are going to perform reg write. So it is on. And our memory read should be in on stage. Why the memory read should be on stage? Because obviously, if we are fetching some information from the data memory, means what it means, we are going to read it. Okay, so from memory we are going to read some data, so it should be on. And memory to register should be on. Yeah, actually we are going to load some data from the memory to register only, no? So this should be on. And here memory write should be off. Why memory write should be off? Because we are not going to store, we are not going to write anything inside the memory. Right now for load, we are going to fetch some data, fetch data from the memory, and we are going to load in the register. Okay. And finally, our reg write data is equal to array of trans instruction. They have passed some instruction, in that we will get the write data, which is taken from the data memory, and it is loaded in the register using reg write data. Okay, so if all these conditions are true, then it will display load operation conducted as expected, else it will provide like error, wrong load operation is conducted, like that. Okay, this is the nature of the scoreboard. It will check, okay, whether the output we get from the DUT is matching with the expected output or not. Okay, Then we have environment. It is easy only, no? Environment will have all these 4 components like generator, monitor, driver, scoreboard. All these components comes under environment. Okay. So we are instantiating, like not like instantiating. We are taking the instance of the generator, driver, monitor, and scoreboard. And here only we are creating in the sense using new. In the UVM we use create, but in SP we use new for the creation of generator and driver, monitor, scoreboard components. For the creation of generator, driver, monitor, scoreboard components, we use new here. See, we are using new here and we are passing the mailbox. Okay, why in the generator we need only mailbox alone, but when it comes to driver and monitor, we need both mailbox and the interface. Okay, you know no why we need both interface and mailbox. Okay, because driver will going to communicate both with generator and with DUT. Same for monitor, it is going to communicate with uh, scoreboard and DUT. Okay, so scoreboard have communication only with the monitor, so mailbox is alone. Mailbox alone is good. Okay, so we have some pre-test tasks which will reset, and some initialization purpose will be done in this pre-test task, and then here is the actual test will happen. All the component have some main task, no? It will be performed here. And we have some wait state here, that is post test. That is after testing, if we need some information, or after testing, if we need to do some operation, do some function, we use this post test. Okay. And see here, finally we have task run. First pre-test will be run, then test will be run, then post-test will be run. After that, it will be finished. Okay. So then we have test. Okay. This test will have environment, and we create the environment inside the test. And here you can notice one thing. See, here we are passing the actual interface, not virtual interface. Okay. Why in the sense? In the architecture itself, you can notice that however we use virtual interface, for final connection between the test bench and the design. Okay, what I am saying is, even though we use virtual interface for our connections between the components, for that like if we have driver and if we have DUT, so both have some connection, no? Through interface, this DUT and driver will have connection using an interface, but that interface is of virtual interface. Okay, so but finally, however we use virtual interface, our final communication and our final connection should be a physical interface. Okay, that is what here it is happening. We are passing a physical interface here. Okay, why physical interface? After that, module is here. See, module is not like a dynamic one like class and all. Okay, it is it will have the physical interface in it. Okay, so this test bench will have physical interface, and this test bench and DUT will communicate. Okay, using that physical interface. Okay, so as of now, do you have any doubt? So we will run and I will show you. See, in the top level, okay, in the test bench top, we are instantiating this uh, test class, and then see here, as I told you, see here they are instantiating the whole design. Okay, so as of now, do you if here anyone have any doubts? See here, we are getting the information. You can notice, no? See this PC current, in the sense it have some address. See that address will be keep on changing, and see we are passing some information. According to the information, it will produce some output. Okay, and the see it is in monitor block, then it will go to the scoreboard. Sorry, actually this is in monitor component, and it will go to the scoreboard likewise. Okay, and you can run this code and you can check. If you have any doubts, you can ask. Okay, so as of now, do you have any doubts or any clarity you need? Hello. No doubt, sir. Hello?
Yes, sir, no doubt.
No doubts, no? Okay. Okay, once again, you can go through this recorded session, or you can, I think the code is shared. You can go through the code and you can confirm and you can verify. You can check once again. And if you have any doubts, you can ask. And wait, I will show you like, okay. And my PPT is visible, no? Throughout the session, my PPT is visible and my voice is clear, no? Throughout the session. There is no disturbance or that
Yes,
my PPT is visible only, no?
yes.
Okay, okay then. Okay, if you have any doubts, you can ask or you can leave. Thank you.